Hello, hello. Am I audible? Hello, hello. Am I audible? Hello, am I audible? अजीब प्रकार के लोग हैं। शुरू शुरू कर देता हूँ है ना? नहीं, अनम्यूट करके रखा था मैंने। रिप्लाई नहीं देता। एक ही है अभी। बीच में एक आया था फिर चला गया। हाँ हाँ हाँ। कुर्सी खतरनाक है, क्या करेंगे? Okay, am I audible? Okay, okay. So let's start then. Good afternoon. Good evening. Sorry. So let us start today's class. So this is the class for the third week. Okay. So basically here we shall now slowly start the our actual aim for what we have taken this course, that is special concrete. So before that we shall be going and briefly studying what is curing and its various types. Okay, and after that we shall start into our we should start briefly start what is special concrete and what is so special about concrete, that type of concrete. Okay, that so that it is different from the conventional ones. Okay, so basically let's begin by studying what is curing. Okay, so curing is basically the stage, okay, where after mixing and after the concrete has been cast, it is stored in a place which is wet, okay, so that the hydration is completed. Okay, because hydration is directly associated with the gain in strength and the proper binding. Okay, so hydration is basically of what? It is basically of alite, because standard cement basically contains the highest concentration of alite, which is basically C3S. Okay, so if we see here, so the reaction or the equation which follows, okay, in the reaction of alite or the hydration of alite is basically this: dxa by dt is equal to k by xa, where xa is basically the reacted layer thickness. This is the thickness, and dxa by dt is the rate of this reaction. Okay, so as you can see here, xa is in the denominator, that is the rate is inversely proportional to the amount of the reaction that has occurred. That is when the process starts. Okay, here, so the xa value will be very small, so the rate of reaction will be very high. But as soon as but as after some time, when the hydration takes place, so the xa value will increase. So after it gets increased slowly, the rate starts decreasing. Okay, uh, after with progress in time. So basically this is the reaction of hydration which is followed. Okay, so the alide basically reacts in water, and the reaction is governed in this way. Okay, so basically this is the sketch of the concrete, which is shown in slash lines, the reinforcement which is given in this uh, blocks. Okay, blocks of this thick lines, and the outer layer is outer boundary is given by the is denoting the formwork. Okay, and the atmosphere is basically nothing but the temperature. Okay, temperature of the concrete, okay, during its casting as well as curing. So this temperature plays a very vital role in concrete, as well as this is one of the main factors which signifies the type of special concrete. Okay, so we will learn this in the coming slides. So basically, let us see what is curing of concrete. So curing is basically the process of maintaining adequate moisture content and temperature in concrete during its early stages of hydration. Okay, so that the cement is hydrated until the desired properties are developed. So it is also important because it prevents moisture loss from the concrete. Okay, and that is important because not only for the consideration of strength development, but also for reducing plastic shrinkage and long-term permeability of concrete. Because if water is evaporated, so that will leave some voids. Okay, so that voids will start in the causing of plastic shrinkage, which results in the you know which results in the crack formation, as well as it increases the permeability of concrete, resulting in its early corrosion. So the gain in strength of concrete occurs due to hydration of cement, which happens only when concrete remains moist with a minimum relative humidity RH of 80%. So this is one of the criteria which is needed to be maintained for proper hydration. And also ambient temperature surrounding concrete should remain favorable. Okay, so for this we need to take into account various conditions, considering temperature, RH, wind speed, etc. Okay, so however evaporation of water from concrete surface is governed by ambient temperature, RH and wind velocity, as we just discussed, and internal water loss. Okay, so that is also known as self desiccation during cement hydration. So these all properties, okay, that will affect the strength gain and dimensional stability. This is basically the plastic shrinkage. So methods, there are various methods of curing. Okay, so the main method, the like mostly used method, is called the wet curing method. So here the concrete surface is kept in contact with water continuously for a particular amount of time. So this can be achieved by ponding, wet hessing, okay, clothes covering, immersion, covering with wet sand, sawdust, etc., etc. This is mainly done in most of the most of the cases in our India especially. But when the surface area is very large, say for example in flat road conditions, so in that cases it may not be possible to completely perform wet curing, or if it if the building, if the structure is not parallel horizontal, it is inclined. Okay, so in that cases that it may be difficult. Okay, so in that case membrane curing is used. So membrane curing basically, here the concrete is covered with membrane for preventing loss of water due to evaporation. So this can be achieved by covering surface with polyethylene sheeting, waterproofing paper, and other various materials which have similar properties. So as you can see in this curve, this plot, so the curing importance in strength development is shown. Okay, so as you can see, the for for the case where the concrete is moist cured, so it develops the maximum strength and it goes on increasing even after 28 days. Okay, as you can see, even in 360, after 1 year also, it is on the process of increasing. But if in the cases where the moist curing has been stopped after certain days, so you will see that after certain time the strength gain is completed, it is stagnant. Okay, it is straight, and that is also dependent on the number of days. Like more the number of days of moist curing, better is the strength gain. That means for proper hydration, the amount of water present is very much important. So uh, those are the main normal cases of curing. Okay, basically wet curing and membrane curing. But for various purposes, it for various purposes and conditions, it may be required for some methods, okay, which can accelerate the process of curing. Okay, so that basically signifies using some application of heat. Okay, so because heat is the main way for accelerating the process of curing. Okay, So application of heat, okay, though it increase in temperature, acceleration the hydration and helps in attaining high early strength, it is also important that it should not be subjected to dry heat, okay. So there should be some moisture, because heating will ultimately result in drying shrinkage or thermal shrinkage, okay. So that also factor has to be kept in mind. We will study in coming slides. So this is because the presence of moisture is very much important, okay. So subjecting the concrete to higher temperatures and maintaining sufficient wetness can be achieved through accelerated curing methods. So because of that only, this concept of accelerated curing is developed, okay. So this is basically wet curing under heating environment, heat environment, okay, higher temperature environment. So high early strength is useful for early formwork removal. This is one of the main conditions because of which this accelerated curing method of curing is popular, okay. But there are also studies concluding that high early temperature may result in lower later age strength and more porosity. So still, this is very much, much investigations are required to, accurately determine how the accelerated method of curing may affect the performance of concrete in a positive or negative way. But majorly it is accepted that acceleration results in early curing as well as proper strength gain, which results in early formwork removal. So there are various methods of accelerated curing, such as one is the steam curing at atmospheric pressure, okay. So in this case, the prefabricated elements are usually stored in a chamber and steam is applied. So steam gas, basically a heated gas, which is having moisture, is applied to the prefabricated elements. So the specimens are here. It is found that the specimens have reported to have slightly higher drying shrinkage and moisture movement, okay. So these are one of this is a negative case, slightly higher drying shrinkage and moisture movement, okay. That may be a positive thing for the hydration. So both things are present, as has been observed in the steam curing case at atmospheric pressure. So this is the plot which has been, this is the regime of heating regime which has been used in the steam curing at atmospheric pressure condition. So the for around 5 hours, it is the delay period after which the heating starts for about 2 hours, and then it 2 or 1 hour, and after that it is maintained for around 15 hours, and after that the cooling process starts, and then it again comes to the normal temperature. So the heating is done about 275 degrees centigrade, okay. So one thing should be kept in mind, that heating should not go above 100, okay, because above 100 the water itself evaporates. So if we go to temperatures above 100 or even above 90, so that may be detrimental, okay. So accelerated methods of curing. So firstly we studied about steam curing at atmospheric pressure, but here we found that although moisture movement will be a good thing, but the higher drying shrinkage is one of the major drawbacks, okay. So to account for that, okay, one more type of accelerated method of curing which has been used is called high pressure steam curing, which is also called autoclaving. So basically both are same, that the steam curing is applied in both cases. The only difference is that this is done in atmospheric pressure, but this is done in high pressure, okay. So when in high pressure steam is released, so that is also known as autoclave, okay, autoclaving, okay. So for this some autoclave machine is used, so which is known as a pressure vessel type curing chamber. So with wet steam should be applied, and the pressure is kept higher than the atmospheric pressure, okay. That is what autoclave is all about, and that is high pressure plus high temperature, okay. So following characteristics can be seen in this case. Firstly, high early strength, then high durability, reduced drying shrinkage, which is the basic advantage as compared to the steam curing at atmospheric pressure, okay. So here it was higher, here it is reduced, okay, lower. And moisture movement is again found, reduce efflorescence, okay, reduce amount of gathering of white particles, and improve resistance to external sulfates. So these are some of the benefits of autoclaving, okay. So apart from that, also there are various techniques such as infrared curing, okay. So this is basically used to increase the temperature of concrete by using some infrared radiations, okay. So this is usually done as can be logically as can be thought about logically. It is basically done in colder climatic conditions, and here rapid gain of strength can be obtained without compromising later age strength. Okay, so it is normally used to cure hollow concrete members. So because you can go inside the inside the structural component or the concrete section, and then give the radiation, okay, pass the radiation into the surface. So that is the basically the advantage of infrared curing when using hollow concrete members. Apart from that, there is also a curing called known as electrical curing. Okay, so basically here current is passed through the fresh concrete between the external electrodes, and that results in the acceleration in curing process. So here one thing should be kept in mind is that alternating current should be used instead of direct current, because direct current may lead to hydrolysis of the cement paste, or basically the breaking of the cement paste. Okay, so because it is direct, so it may result in the breakage. So therefore alternating current should be used in the process of electrical curing. uh, According to ASTM-C, this one 684/99 2003, these four methods are used to predict the 20th day strength of concrete. Okay, so one is the warm water method, which can be denoted as method A. So here water bath is used to conserve the heat during the hydration. Okay. Second is called the boiling water method, which is the method second B method. Here boiling water bath is used to provide additional heat. Okay. Third is the method C is the autogenous curing. Okay. So here curing takes place under some adiabatic conditions. Okay, and fourth is the high temperature and pressure, which is the autoclave. Okay, so the method D, so here external heat and high pressure are supplied. Okay, so this is as per ASTM C 684/99 2003. Okay, so this basically has the characteristics of all the this one autoclave, infrared, electrical curing, all the components. The this one the specialties, these four methods have some way or the other. So okay, so they are basically classified a little bit differently, but the main motto is almost the same. Okay, so curing compounds. Okay, so various types of compounds are used. Okay, so these are basically used in the membrane curing. So these are the membrane forming compounds which are sprayed on the surface of fresh concrete. Okay, so they possess wax, natural resins, synthetic resins, solvents, okay, which are having high volatility. So these compounds have a efficiency based on the extent they permit the loss of water per unit surface area, because that is the main reason why it is being used. Okay, and ASTM C309 deals with the specifications and testing of this compound. So for finding out various characteristics, specifications, and also tests involved to determine its quality, we can refer to ASTM C309. So these are some of the curing compounds, okay, which have been used in the membrane curing. Okay, so this is wet curing basically. This is membrane curing, and this is spraying of some curing compound. Okay, which is also a type of membrane curing itself. So now let us come to one more important parameter, which is called as maturity. Okay, concrete maturity of concrete. So as strength of concrete depends, it has been found, as we can understand, that strength of concrete, it depends on two factors. Okay, one is the age, okay, and second is the temperature. So both result in a significant development of strength, and both are proportional, okay, to strength. So therefore it can be taken that the strength is a function of maturity. Okay, so what is maturity? It is nothing but the summation of the time interval and temperature. Okay, so generally the time interval, it is considered in hours, and temperature is basically the temperature of the concrete, okay, with respect to some datum temperature. Okay, so that can be any temperature, but it is usually taken as -10 degrees centigrade. Okay, here as per some relevant codes, it has been accepted as -10 degrees centigrade. So batches of the same concrete mixtures of same maturity will attain the same strength. Okay, regardless of the time temperature combination. So if we say that for a particular concrete mix, and which is having a same value of maturity, so irrespective of what is the time temperature combination, okay, more time less temperature, less time more temperature, the if the maturity is same, then the strength will definitely be same. Okay, so these all concepts related to this maturity is present in ACI 306 R88 and ASTM C 1074. Okay, so this can be used to check the curing of concrete and evaluate the strength development process. So with this we come to end of the curing. Okay, the topic of curing. So now we will be going, we'll be basically starting our main main field, main topic field, which is basically main domain, which is basically special concrete. Okay, so at first we will go through what is cold weather concreting. Okay, so the basic question which till now I think most of you have thought about is, what is that which makes a concrete or concreting operation special? Okay, so why it is called special concrete, why it is not a normal or conventional concrete? Okay, so as you can see here, so there is a certain range of variables over which the process or operation is called normal. Okay, so this, if you can check the codes, say for example in our case, if you check IS 456 or even IS 10262 mixed design, so if you see there are some parameters, okay, beyond which we can vary. So that is because that those are the ranges for a concrete to be called as normal. Okay, but if any of the processes, okay, out of these six steps, okay, in the preparation of concrete, that is batching, mixing, transportation, placing, compaction or curing, okay, out of this, if any of the processes go out of range, okay, or some other some special process type of special process becomes involved, okay, in the you know in the process of manufacturing of concrete due to the requirement of that condition. Okay, so then the concrete has to be treated as special. Okay, so that is the reason which separates a normal concrete from a special concrete. Okay, so let us see, like for example, if we are talking about cold weather concrete, so this is special because it is cold. Okay, so as we will see now, we will find that cold weather concreting, if we follow the steps as similar to the conventional concrete, so there will be a lot of problems. Okay, so we will see why it is special. So special concrete, if one or more of the following, okay, conditions fall outside the normal range, the conditions being materials, environmental condition, properties, placement methods, placement conditions. So if any out of them is different or outside the normal range, so that is termed as the special concrete. Okay, so the conditions, basically here we are going to study the temperature condition. Okay, so how temperature condition can be used to separate a conventional concrete from a this one special concrete. So here we mean to talk of uh, in case of conventional concrete, okay, the normal range of ambient temperature is the criteria where the concrete can be placed normally. Okay, so in both sides of this range, we need to carefully consider the implications and address issues related to all aspects of the concreting operation, because the behavior of the concrete beyond this range will be little different. Okay, so we does have special conditions arising out of cold weather and hot weather. Okay, that's why it is it becomes special. So special concrete. So now let us see the this is the criteria. Okay, the criteria which determines what is a cold weather concrete. Okay, so what is basically a cold weather concrete? As per ACI 306, cold weather concrete is defined as a period. Okay, cold weather is basically defined as a period when for more than 3 consecutive days, the average daily air temperature is less than 5 degrees centigrade and the air temperature is not greater than 10 degrees centigrade for more than half period of any 24-hour period. So if for more than 3 consecutive days the average daily temperature is less than 5, and for any 24-hour stretch more than half of the time the air temperature is not greater than 10 degrees centigrade, so then we can define that weather to be as a cold weather in terms of cold weather concrete. Okay, as per ACI 306. So why this is important? Okay, this is important because this is a temperature where the freezing of concrete will occur. Okay, so what happens when concrete freezes? So then the conditions what the impact how the freezing of concrete will affect its behavior is such that pore water in concrete will start to freeze. Okay, there will be a change in the chemistry of pore water, and as the cold weather will sustain, the hydration will basically stop. Okay, so that means strength development of concrete is affected adversely, and because the pore water will generally freeze. Okay, so we know from science that the volume occupied by water is lower than the volume occupied by ice. Okay, so due to freezing, okay, the pore water will occupy 9% more volume than the you know the freezing water will occupy more 9% more volume than the actual water. Okay, and that will be detrimental to the long term integrity of concrete, which is basically called as freezing. Okay, freezing thawing condition. Okay, so that is the main problem associated with freezing. Okay, firstly, the reaction, the rate of reaction is slowed down or it is completely stopped, and secondly, because of the increase of the pore water volume, because of becoming of ice, the inner voids will be much larger, which will impact the long term integrity of concrete. So here you can see the effect of cold weather. So this the age at freezing, it plays a very important role. Lesser is the age, more is the increase in volume because of the amount of water present. Okay, and more is the increase in volume, you know uh, higher is the hampering in the long term properties. Okay, long term integrity of the concrete. And here you can see the relative setting. Okay, even even with using of accelerator, okay, still the setting time is very high. Okay, as compared to here, the 21 degrees centigrade, if you see here, it is more than the double. Okay, at -1. Okay, even with the use of accelerator, so it adversely impacts. Okay, so it is having a very detrimental effect. And here also you can see that with age, okay, the strength development will be less. Okay, at 73 degree Fahrenheit, that is at normal temperature, the rate of hydration is much more as compared to 55, or very more very it is very higher as compared to 40 degrees. So the rate of hydration is very less. Okay, so which will also result in long time for setting. Okay, and hydration. So here, as you will it has been plotted, the effect of temperature on setting time of concrete. So as you can see, around 30 degrees centigrade, the setting time is basically 1 to 2 by 3 hours. Okay, so which is basically in our place. Okay, like in India, it generally happens in the summer season. So as you decrease the temperature, okay, it also starts increasing. Okay, so at -1 degree centigrade, it is the highest. It is it is more than 19 hours, and after -7, it will never set. Okay, that means the hydration has completely stopped. Okay, and by viewing this chart, you can see, or you can also take it as a thumb rule, that for every 10 degree centigrade reduction, okay, the setting time of concrete will almost double, as you can see here. So 27 degree, it was 4 hours, but as soon as you decrease it by 10, almost 10 degree, say 16 degree, it got double. Okay, 4 to 8. Okay, then similarly from 16 to, if you say around 6 degree, it will again almost be double, like 14. Okay, it is close to 16. So that is the thumb rule. Okay, every 10 degree centigrade reduction will double the setting time of concrete. Okay, so because of this, okay, so lot of problems are associated with cold weather concrete. Okay, so as you can see here, the resistance to frost coefficient, it almost becomes zero when the degree of saturation is more than 90%. Okay, that means the concrete has started to freeze. Okay, so this damage, okay, can be prevented. Okay, at early ages by maintaining by taking some conditions. Okay, by employing some techniques. Okay, to control the environment of concrete till it reaches 3.5 megapascal strength. Okay, so if we can reach, as per ACI 306, if we can maintain the temperature condition of concrete till it reaches a strength of 3.5 megapascal strength, then we can prevent the damage of concrete due to freezing at the early stages. Okay, so that is very important factor. Okay, for preserving the strength of concrete and not adversely impacting at early ages due to freezing. So these are based on the discussions, these are some of the concerns which are associated with cold weather concreting. So firstly, we need to prevent the damage to concrete due to freezing at the early stages. Secondly, we need to ensure that the concrete develops required amount of strength for the safe removal of formwork. Okay, because formwork is mainly used for giving it the shape. If the strength is not developed, so definitely the shape will also not be developed. Okay, so no use of the formwork provisions. Okay. Thirdly, we need to maintain curing conditions so that faster the normal strength development is possible without any excessive heat. Okay, so that is one of the criteria important. Then we need to limit rapid temperature changes in the concrete to prevent thermal cracking. Okay, because if the alpha value changes, that is a thermal expansion value, so that may also result in cracking. Okay, at different segments. And fifth, we need to provide protection in the concrete in a manner and extent that its performance over the intended service life of the structure is not adversely affected. So this is basically a long-term protection. Okay, so we will see all those parameters. So as we saw that, as a thumb rule, for every 10 degrees centigrade reduction, the setting time of concrete almost double. So thus duration over which concrete is vulnerable to damage due to freezing increases. Okay, so you know so more is the this one the duration over which the concrete is frozen, the damage is automatically increased. Okay, because of the setting time increase. So it should be remembered that when warm concrete is placed on cold subgrade, it will lose heat and its temperature will drop because of low temperature. Adequate precautions need to be taken during curing to ensure that the concrete is not damaged in early stages and hydration is allowed to continue, which will ensure appropriate strength development. So this is the criteria we have to follow. Okay, to ensure that at least 3.5 megapascal, as we saw, that amount of appropriate strength is developed to counter the damages, okay, occurring due to the freezing at colder temperatures. Okay, so we will see how it can be done. Okay, so concrete protected and properly cured matures to its potential strength despite subsequent exposure to cold weather. Except in heated protective enclosures, little or no external supply of moisture is required for curing during cold weather, because here the this one is evaporation problem is not there because it is a cold weather. Okay, so there is no external supply of moisture required. Okay, uh, except if we if we artificially heat the concrete members. Okay, concrete placed during cold weather will develop sufficient strength and durability to satisfy intended service requirements only if it is properly produced, placed and protected. Okay, and at other temperatures also, even though it may not be defined as cold weather, appropriate protection, especially during the first 24 hours to avoid freezing, is required. Okay, so this one. So let us see how the acceleration of hydration can be done in cold weather. Okay, so the reduction of setting time and the acceleration of strain gain often result in substantial savings due to shorter protection periods, faster form reuse, earlier removal of shores, and less labor in finishing flat work. Okay, so these are the these are some of the main advantages of using accelerated hydration. Okay, setting time is more important in flat work finishing. Okay, because we need to we need to quickly work upon that. Okay, so that it needs to quickly stiffen so that we can work upon that. Okay, we can do further construction. Early strain gain is more important for early formwork removal. Okay, so this acceleration may be some of the techniques may be such that we can use some general purpose cement and cement with moderate sulfate resistance with in 20%. Okay, and then mix it with some type 3 Portland cement, which is general purpose cement with finely ground particles. Okay, this fine is important because this will accelerate the rate of hydration. Okay, and apart from that, we can use some state accelerating admixtures. So this type of techniques can accelerate the process of hydration. So apart from that, some of the planning practices which are recommended are such that prior to pour, we should clearly define the cold weather concreting methods which can be used or which will be used. And we need to we need to meet we need to have a pre-placement meeting with the contractor, producer, specifier, laboratory, and other third parties, so that it is quite efficient and it is also saving our concrete from the ill effects of cold weather. Okay, And where a specified concrete strength must be attained in a few days or weeks, protection at temperatures above 10 degrees centigrade or 50 Fahrenheit is required. Okay, so if that is very important, that the concrete strength should gain at a specific time, days or weeks. So we have to keep that temperature above 10 degree. We have to install some techniques for that. Okay, so temperature records. Temperature of concrete determines the effectiveness of protection regardless of air temperature. Maintaining temperature records of concrete in place is essential. Okay. So because of that, okay, it is very important to find the concrete temperature and its effectiveness against, due to protection. Okay. So exposure to freezing and thawing. Okay, so one of the main ways, okay, how it can be, it can be countered is by air entrainment. Okay, so concrete should be air entrained if it is likely to be saturated, and saturated means completely freeze and exposed to freezing and thawing cycles during construction or during service. Okay, so because of the presence of saturated, that is water, and exposed to freezing and thawing cycles during construction, so that will result in cracks, okay, and increase in volume. So best way to counter that will be using some air entrainment admixtures. So apart from that, slump, okay, lower slump and lower water cement ratio mixes are particularly desirable in cold weather for flat work. This reduces bleeding as well as decreases setting time. As we know that, you know uh, more will be the water, lesser will be the water cement ratio, and more lesser will be the water cement ratio. Okay, more will be the strength gain, as well as, quickly the concrete will set. Okay, and also in cold weather, because there is no loss of water. Okay, lower slump is, sufficient. Okay, so that will also help in our cause. And apart from that, truck travel time, the distance from the plant to the point of placement can have a severe effect on the temperature of concrete. So if the distance is quite high, or the place is very far away, so at that time, you know uh, during the this one uh, during the traveling of the truck from the site, from the RMC plant, okay, to the site, so that at that time only the concrete may freeze. Okay, so those are some of the important parameters which have to be kept in mind. So temperatures for placement and protection in cold weather, cold weather. So for this one, for placement and protection in cold weather, against cold weather. So for this, ACI 306 provides some recommendations, okay, which we can follow. So basically these are some of the recommendations, which will be shown in a much tabulated way better in the next slide. So as you can see here, more is the, for more, for higher size dimensions. Okay, so minimum concrete temperature is can be reduced. Okay, so that means lesser is the dimension, okay, more has to be the temperature of concrete. Okay, and also lower is the temperature, okay, higher has to be the temperature of concrete. Okay, so both these factors have to be kept in mind, as you can see in a much better way here. So let us say the condition of, greater than 1 degree centigrade is denoted by A, minus, temperature greater than 1 is denoted by A, greater than minus 18, temperature between minus 18 to 1 is denoted by B, less than minus 18 is C. Okay, then minimum temperature of this one, fresh concrete as placed and maintained is D, and maximum allowable gradual drop in temperature in first 24 hours after end of protection is E. Okay, so here if you see that, then more, lesser is the temperature, more has to be the concrete temperature. Okay, and also higher is the thickness of section, okay, lesser can be the temperature of concrete. Okay, so these two factors have been found here as per the ACI 306 conditions. Okay, this table is taken from there. So preparation before concreting. Okay, so what are the preparation steps which you have to keep in mind before the concreting process? So all snow, ice and frost should be removed. Okay, concrete should not be placed on frozen subgrade, it must be thawed, okay, or heated, and if required compacted. So this thawing can be done by steaming or spreading a layer of hot sand gravel, or removing and replacing with unfrozen fill, covering subgrade with insulation for a few days, or using heaters under insulated blankets. We will see the picture of this as an example. So temperature of surface in contact with fresh concrete should be at least 2 degrees centigrade, but not more than 5 degrees centigrade higher than concrete temperature. So as compared to the inner concrete temperature, the surface should be at least be greater than 2 degrees centigrade, but not less than not more than 5 degree, because if it is more than 5 degree, that also may lead to some segregation, okay, because of different alpha. So this is the these are the steps which you have to keep in mind, okay. So heating of constituent materials. So we can also use some heating techniques in the constituent materials, say for example in water. So here the temperature of water may be raised to about 80 degree, but it should not be more, because if it reaches 100, the water will boil, okay, so it will evaporate. So it can be reached up to 80. Pipeline and storage tank need to be properly insulated to avoid any heat loss from the water till it reaches the batching plant mixture, okay. So those techniques can be used. So firstly, it can be heated to 80 degrees centigrade, and also the pipeline storage should be insulated so that there is no water loss due to heating, okay, till it reaches the batching plant. And and also so that the water is not cooled, okay, so till it before it reaches the batching plant, otherwise there is no no use of heating, okay. And these are some of the criteria which can be used in water heating. Similarly, some criteria which can be followed for heating the aggregate, they are firstly coarse and fine aggregate, they can be frozen, okay, having lumps of ice in them. So uh, because of cold weather, coarse and fine aggregate may develop some lumps of ice, okay. So those aggregates must be thawed before batching, okay. So they need to be heated, and the maximum temperature to which they can be heated should be also clearly defined, okay. Otherwise here also cracks may develop in the coarse aggregate basically. So conveyor belts, batching plant bins have to be properly insulated so that it is not frozen, okay. So these are some of the storages, okay, which can be used for aggregate storage. So as you can see here, is completely insulated, okay. So this insulation prevents it from getting freeze, okay. So some of the points which can be used during curing protection period are: as long as forms are in place, that is the forma is in place, concrete adjacent to the forms also retains some moisture, okay, due to the contact. So the exposed horizontal surfaces are very susceptible to rapid drying in a heated enclosure, okay. This, because of the heating, they are also susceptible to rapid drying. So curing compounds may be recommended to prevent drying of concrete, okay. So these are also essential. And steam curing and water curing may be done, but should be stopped well in advance of protection period. Such treatment make the concrete nearly saturated, and if the protection is withdrawn, the likelihood of freezing also increases, because the concrete, due to water curing and steam curing, it will become saturated, and if the protection is withdrawn, okay, so at that time only the freezing condition will increase, okay. So that's why it should be stopped well in advance before the installation of protection period, okay. So curing of concrete after protection period. So extent of drying in concrete depends on temperature of concrete and ambient air, wind speed, and relative humidity. So this protection period is basically the, as we discussed, it is the period till the concrete basically gains the early strength of around 3.5 megapascal as per ACI 306, okay. But after the early hydration or early stage, after that also the extent of drying in concrete, that will depend on temperature, air, ambient air, wind speed, relative humidity, etc., okay. And it should be seen that the limiting evaporation rate, okay, should if it should be less than 1 kg per meter square per hour. If it is more, then protective measure has to be installed, okay, again. And using curing compound, or you can we have to use some curing compound or some impervious cover as the protective measure. Water may be normally be used also if no further freezing is expected, that is cold weather condition does not prevail, okay, during till the curing period is over, okay. These are some of the plots which you can see for further understanding, okay, as per ACI 306. So recommendations for cold weather concrete, okay. So these are basically the recommendations which ACI 306 has provided, okay, for concreting in cold weather. So here according to them, the ambient temperature should be above 5 degrees centigrade, okay, so that it becomes a normal condition. If that is the case, then material does not need any type of heating. Okay, placement temperature should be maximum of 12 degrees centigrade, and if that is true, these two conditions are true, then insulation is not required, curing during protection is not required, protection time is also not required, and after protection the curing can be a normal water concrete, normal water curing. So this can be all possible, that is nothing will be required, and it will be all normal if the ambient temperature is 5 degree above, that is normal, and placement temperature is maximum 12 degree. Okay, so that is the thing, if above 5 degree. But if it is between 0 and 5 degree, okay, then what we have to do is, then material, in material we have to heat the water. Okay, water needs to be heated, and placement temperature should be at least 7 degrees centigrade. Okay, so that concrete can be protected from freezing. Apart from that, insulation, for insulation, mineral fiber blankets has to be installed with thermal resistance of 0.224 meter square Kelvin per watt per 10 millimeter thickness. During protection, curing is not required. During curing, protection is not required. Sorry, and the time of protection for OPC will be 72 hours at 5 degrees centigrade, 46 hours at 10 degrees centigrade, or 3.5 megapascal can be reduced up to 25% using accelerator. So these are the time of protection. Okay, so if it is 5 degree, it has to be, you know uh, 72 hours. If it is 10 degrees centigrade, it is lesser, 46 hours. And if 3.5 megapascal, out of this whichever is fast, found initially, like whichever is the minimum. Okay, so that is the time required for protection. Okay, and if we are using accelerator, it can be reduced to further 25%. Okay, or it can be reduced up to 25%. So after protection, after curing, also if there is a protection required, we have to see. So no curing is required if rate of evaporation is less than 1 kg per meter square per hour, just as we discussed before few slides back. But if it is more, then we have to apply some curing compound. Okay, so water can be used if freezing is not expected. So these are the conditions that has to be kept in mind if the ambient temperature is between 0 and 5 degree. So these are some of the recommendations for cold weather concrete as per ACI 306. So here basically the insulating blanket thickness has been provided in millimeter. Okay, as per at ambient temperature. Okay, those are 0, 5, -5 and -10 degrees centigrade. So thickness of insulating blankets having thermal resistance of 0.224 meter square Kelvin per watt per 10 millimeter thickness to has to be used to maintain the concrete temperature at 10 degrees centigrade. Okay, for 3 days. So this is the condition for the concreting at 10 degrees centigrade temperature for 3 days. Okay, apart from that, if we are concreting from 0 at 0, -5 and -10 degrees centigrade, we will see that the insulating blanket thickness will reduce with the increase in cement content. Okay, more is the cement content, so it will get reduced. Okay, and the concrete thickness also, as you can see, more is the cement content and thickness, it is reduced. Okay, but lesser is the temperature, it is increased. Okay, so it is directly, the thickness will be it will be lesser for increase in cement and thickness of concrete, and it will be more for reduction in temperature. Okay, so achieving strength in stipulated time. Okay, why it is required? It is required for the safe removal of formwork, for any specific early strength requirements, for safe loading of the structure during and after construction. Okay, so these are the main criteria, main reasons for which the strength should be achieved in a particular fixed amount of time. Okay, and how can it be done, achieved? So this can be achieved by using higher cement content. Okay, why? It is because the more will be the cement content, so the W by C value will reduce. Okay, water by cement will be less, and as we know, water by cement is inversely proportional to the strength, so lesser will be the W by C, increase will be the strength. Okay, so that way strength can be achieved. Second can be the use of accelerating admixtures. Okay, so that will increase the rate of hydration, which will increase the strength. And third is by maintaining higher temperature for increasing the hydration. Okay, so these two influences the amount of hydration, and first actually results in lower W by C value, which increases the strength. Okay, So yeah, so in situ strength, as per the maturity concept, okay, so as per the maturity concept also, it has given the strength, like we can, we can plot strength with respect to maturity concept, as we will see in the in the coming slides. So strength gain of concrete is a, as we discussed, is a function of time and temperature, okay. The strength development estimation can be made by relating time temperature history of field concrete to cube strength under standard conditions in lab, okay, such that by following this relation, m is equal to summation t minus t naught into delta t, okay, where m is the maturity factor, okay. This is expressed in the unit of degree hours. T is the temperature of concrete, okay, which is expressed as degree centigrade. T naught is the datum temperature, as we discussed earlier. It has been assumed minus 2 minus 10 degrees centigrade as per ACA 306, but it can vary also, okay. And delta t is duration of curing period at temperature T, okay, which is also expressed in R, okay. As you can see here, it is a plot between the compressive strength in megapascal as respect to maturity factor in terms of degree centigrade R, okay. So we can almost see it to be a straight line, okay. It is linearly increasing. So around 1000 maturity, it is around 3.5, and around 10,000 it is around 10 megapascal, okay. So like this also we can find the relation between compressive strength and maturity factor. So here to here there is a, there is a table, this various values of how the compressive strength is, dependent on the maturity factor, and the its parameters, namely the r's and the t minus t naught value, time interval. So all those factors have been tabulated here, as you can see, for determining the in situ strength of concrete. Here if you can see, the t naught value is minus 5, okay, not minus 10, as you can see here. So that's why the value is 15, not 20, okay. So but if it is not mentioned, we generally consider it to be minus 10, okay. But here, as you can see, it is minus 5, okay. So yeah, so as you can see, these are the r's, this is the temperature, and we have, using this we have used the summation t minus t naught value and found out the various values. And by adding we get the total, okay. So by summation we get the total, and after that we can relate this with megapascal, okay. So this is around, so as I told you, it is around 3.5 for 1000, as you can see here, okay. So yeah, for cold weather concreting, these are some of the live examples they have done. So here enclosure has been given, okay. Here, as you can see, it has been erected, okay. So this allows the protection of concrete, okay, uh, which is here, okay. And the concrete walls are covered by membrane. So as you can see here, it is also the walls have been covered by membrane, and some enclosure has also been provided to protect it, okay, in a erected format, okay. And here you can see the curing compound. Here some membrane curing has been done by spraying on concrete, okay. So this also preserves the concrete from cold weather, okay, in curing. Here you can see, in this case, concrete footing, okay, pedestal being covered. This is the thing, this is the pedestal. So concrete footing pedestal, it has been covered with a tarpaulin. This is the tarpaulin to retain the heat of hydration, okay. So it has been covered like we covered cars, okay, in garages. So here the concrete footing has been covered in the pedestal with a tarpaulin to retain the heat of hydration. And here, when suitable preparations to build enclosures and insulate equipment have been made, so cold weather is no obstacle to concrete construction. So here they have done construction in ice, okay. So from this, as we can see here, so it is explaining, or it is giving us advice that when suitable preparations, okay, and insulating equipments are used, okay, by building enclosures and other things, so then cold weather is not an obstacle for the construction of concrete, using concrete, okay. So that is the factor. So cold weather, it will not hamper if we adopt proper practices. Here we can see that stack of insulating blankets, okay. So these blankets trap heat and moisture in the concrete, providing beneficial curing, okay, in the form of this one, membrane curing, okay. So mostly membrane curing is used in case of this one, cold weather, okay. And here inside, okay, inside some, this one, heat is there under the slab, okay. So finishing this concrete, this is a flat work basically. So concrete flat work has been finished, okay, and finishing has been done, and it can be proceeded using a windbreak, okay. So some facilities have been given which can break the wind, okay, the flow of wind, and there is adequate heat under the slab, okay, and the concrete has also low slump, okay. So low slump will result in higher quick hydration and quick stiffness, okay. uh, After that, you can also see here examples of tarpaulin, heated enclosure maintains, okay. As you can see here, adequate temperature, this maintains adequate temperature for proper curing and protection during severe and prolonged winter weather, okay. And apart from that, you can also see that polyethylene plastic sheets admitting daylight are used to fully enclose a building frame, okay. The temperature inside is maintained at 10 degrees centigrade, 50 degree Fahrenheit with space heater. So if it is very less, we have to go around 10 degree, okay, above 10 degree, as we saw in the last slides, okay, as per ACI 306. So here you can see, with when you see this, as we studied in one of the tables, that hydration stops completely if it is below -7, okay. So but they have done concreting, achieved concreting in air temperatures even down to -23. So it is even very 16 degrees lower than -7 when the hydration stopped, okay. Still they have done concreting successfully. How? Because the concrete was cast in this insulated column form, which was made of 19 millimeter high density plywood in the interior, okay. Then 25 rigid polystyrene in the middle, and 13 rough plywood outside, okay. So it is around 25 plus 19 plus 13. 19 plus 13 is around 32. 32 plus 25 is 57. So 57 millimeter of, like, approximately 6 centimeter thick formwork has been given, okay. So this thick, if you give forma, so that can even sustain air temperatures of as low as -23, okay. So that is the capability of using membrane curing, okay, in cold weather. So here also you can see in this place, this picture in the left, you will see that some kind of hydronic systems have been used here, okay, with hose laying on soil to defrost the subgrade, okay. So for defrosting, by flowing of some gases or liquid. So here the subgrade has been defrost, okay. And in the right picture you can see, like, warming from forms, okay. So something has been, some chemicals or some materials has been added, okay, which can warm the forms while fresh concrete is pumped in, okay. So that the appropriate amount of temperature is maintained, okay. So these are the special types, okay, special conditions, special criterias, and special techniques, as well as special methods which can be used for concreting in cold weather, okay. So that's why it is a special concrete, okay. Now let us go to the second type of special concrete, which is in the case of hot weather concreting, okay. So yeah, so let us take a recap. So in cold conditions, what we found was, we talked about freezing, okay, where the poor water started to freeze. There was change in chemistry, okay, due to freezing, and the strength development got badly affected because it stopped, okay. And the ice had a volume of 9% more as compared to water, which resulted in this one, shrinkage, okay. And it was detrimental to long-term integrity as well as permeability, okay. But in case of hot weather, okay, how is it affected, okay. So we will go through now the impact of concreting, okay, during hot weather. So basically, what is a hot weather? Hot weather is a combination of some of the following conditions, okay, that are known to impair the quality of fresh or hardened concrete, largely by way of accelerating the rate of moisture loss, okay, and rate of cement hydration. So mainly these two factors are affected due to hot weather. One is the acceleration rate of moisture loss, okay. uh, like these two affects the quality, okay. So one is the moisture loss acceleration, okay, due to hot weather, and second is the rate of cement hydration, okay. So this, like, it is so high that it also adversely affects the quality, okay. So the considerations include these are the main factors, okay. which is defined as hot weather. Firstly is high ambient temperature. Okay. Secondly is high concrete temperature. Thirdly is low relative humidity, and fourthly is wind speed. Okay, these four parameters characterize what we call as hot weather. Okay, so curing of concrete after protection period. So extent of drying in concrete, it depends on temperature of concrete and ambient air, as we studied, wind speed and relative humidity. A rate of evaporation higher than 1 kg meter square per hour may call for special protective measures, as we studied, such as use of an appropriate curing compound or an impervious cover. Okay. So the hot weather at the time of mixing, okay, or placing, or at the very early age, okay, affects the concrete in both ways. These two ways. One is in fresh state and the second is in hardened state. Okay. So how it will affect, we will now study. So in fresh state, okay, what happens is due to evaporation, okay, there is increased water demand, okay, because the amount we have added, that amount slowly it actually at a faster rate only as compared to ambient, it starts to evaporate, okay, and this results in the increased rate of slump loss. Okay. So thirdly, this also results in poor finishability because cracks will develop, and increased tendency for plastic shrinkage cracking as well as thermal cracking potential. Okay, and increased difficulty in controlling air entry and air content. Okay, because so much cracks will be developed that we don't need entrainment. Okay, so it will be entrapped air. Okay, so because of cracking, lot of air will be air content will develop. So these are some of the criterias which affects in fresh concrete. Okay, in hardened concrete, what happens is lower 28th day and later strengths come, resulting from high water demand, because as the water cement will increase, because we are pouring high water, so definitely the strength will reduce. Okay, and higher concrete temperature. So due to higher water demand, higher concrete temperature, the lower 28th day and later strengths will develop. Okay, decreased durability. Okay, that will also result due to cracking. Okay, so more will be the cracking, more will be the permeability, and that will result in a larger ingress of chloride ions, which will result in corrosion. So increased permeability as a result of high water content, in inadequate curing, carbonation, lightweight aggregates, or improper matrix aggregate proportions. Okay, greater variations in surface appearance, okay, due to cracks formation, decreased abrasion resistance also, because we will be sprinkling water to facilitate the finishing as the water will get evaporated. Okay, and there will be increased tendency for drying shrinkage. Okay, and differential thermal cracking. Okay, so lot of cracking mechanisms will occur. Okay, drying shrinkage cracking, plastic shrinkage cracking, thermal cracking. Okay, so these are the some of the ill effects of hot temperature. Okay, so in cold temperature, the problem was ice. In hot temperature, it is due to more amount of water required and the cracks formation. Okay. So here, yes, as you can see here, you can cracks in concrete due to hot weather. Okay. So as you can see, observe here, these are various types of plastic shrinkage cracks which are occurring. Okay. So plastic shrinkage cracks are occurring, drying shrinkage cracks, and also thermal cracks. All types of cracks will occur, which will result in increase in permeability and more amount of ingress of chloride ions, resulting in corrosion. Okay. So working with hot weather concrete. Okay. So how to now find out mechanisms which can bear all those problems and give us some sustainable solutions. Okay. So moisten concrete aggregates, okay, that are dry and absorptive can be used. We have to keep the concrete temperature low by cooling aggregates and mixing water. We have to dampen the subgrade and forms prior to placing concrete. We have to erect temporary windbreaks, okay, to reduce wind velocity over the concrete surface, and we have to erect temporary sunshades to reduce concrete surface temperatures. Okay, so the main motto will be to reduce the temperature. Okay, in cooling, in cold weather, we have to, our intention was to increase the temperature, and here we have to decrease the temperature by adopting various strategies. Further strategies can be using materials and mixed proportions that have good record in hot weather conditions. Okay, which performs much better as compared to the rest. And we can organize a pre-construction conference to discuss the precautions required for the project with the manager and all the concerned contractors and all the concerned people. It is often recommended to have trial batches of concrete and mock-up exercise to validate assumptions and ensure quality construction. Okay, so we need to perform some mock-up, mock testing, mock concreting, and all those, so that our assumptions are valid and the quality control is established. Okay, so now let us come to the water requirements. Okay, so as we studied, higher water temperatures cause higher concrete temperatures, and hence more water is needed for the same amount of slump. Okay, the extra water decreases the strength, durability, water tightness, and other related properties of concrete. Okay, so that is basics. So drying shrinkage generally increases with total water content. Okay, so concrete cast in hot weather is also susceptible to thermal shrinkage as it subsequently cools. Okay, so here three types of shrinkage will occur. One is drying, one is thermal, and one is plastic. Okay, so drying and thermal are the main shrinkages which are directly associated with hot weather concreting. Okay, so this is mainly occurring initially, and this is thermal shrinkage as it subsequently cools down. Okay, so effort should be made to use cooled water as it will reduce the concrete placing temperature and also help in reducing the water demand for a given level of workability. Okay, so cooling of water is one of the very imperative conditions which can be used. Okay, ice, in that regard, ice which can be in crushed form, shaved form, or chipped form, when placed directly into the mixture as part of the mixing water, it can reduce concrete temperature. Okay, so if used, ice should be 75% of the batch water requirement. The ice must be not be melt, okay, before it is placed and in the mixture, but must melt completely prior to the completion of mixing of concrete. So the ice should be used about 75% of the batch water, and it should be such that it should not melt before it is placed in the mixture, okay, but it is completely melt before the completion of the mixing. Okay, so that our all the criteria are satisfied. Substituting ice, as you can see here, ice has been substituted for the mixing water substantially, and this lowers the concrete temperature in a very good way. Crusher delivers finely crushed ice to a mixer reliably and quickly, as you can see in this diagram. So now let us see the effect of cement. Okay, cement type affects the hot weather performance of concrete. Generally, use of slower setting Portland cement may improve the handling characteristics of concrete in hot weather. Okay, so this is beneficial cement in hot weather, but it is not that beneficial in cold weather. Okay, when using slower hydrating cements, the slower rate of heat development and the simultaneous dissipation of heat from the concrete result in lower peak temperatures, leading to less thermal expansion and reduced risk of thermal expansion. Okay, so the thermal thermal shrinkage, okay, so that can be controlled a lot by using slower hydrating cements because of lower rate of heat development. Okay, so cement content should be limited to that required to provide strength and durability. So lesser is the cement content, okay, more we can replace it with some admixture, it is better. Okay, because there will be less generation of heat due to hydration. Okay, so cement content should be limited to that required to provide strength and durability, as temperature increase from hydration of cement is directly proportional to cement content, as we discussed. Concretes that have high strength at early stages also tend to develop high concrete temperatures because of faster hydration during the initial curing. Such concretes therefore should be provided thermal protection to ensure gradual cooling, because the temperature is already higher. If you also go into high strength development, it will further increase the rate of temperature. Okay, and that will result in further this one, it will result in your thermal expansion. Okay, and that will result in thermal shrinkage. Okay, so for that it is better to gradually cool and ensure some thermal protection. Okay, let's now see how the aggregates can be controlled. Okay, so how can be aggregates can be cooled, or what can be done to the case of aggregates. So gradation, particle shape, etc. of the aggregate should be such that the water demand is minimized. Okay, because then that also lowers the water required. Okay, and blending of aggregate may be considered. Okay, so we can mix aggregate with some other admixtures. Okay, so which can be like some green materials, waste materials. It may be remembered that whereas on the one hand crushed coarse aggregates contribute to higher water demand, they also provide better resistance to cracking on the other. So this is a tricky situation. So where if we use crushed coarse aggregates, okay, so that will, that will contribute to higher water demand because more water demand is required. So that is a negative, okay. But the positive is that it has a better resistance to cracking, okay. So we need to finally find the net, okay, net outcome. Like is it after plusing and minusing, is it finally is it productive or counterproductive? So that is the thing we have to take into account, okay. So as we studied, like we need to reduce the amount of cement content, okay. So how to reduce? By using some admixture or by using some SCM, okay. So admixture is basically chemical admixture. As we studied in the earlier classes, it is basically used to reduce the water content, and mineral admixtures are basically used to decrease the cement content, okay. So one of the mineral admixtures which can be used are, it is called as the SCM or supplementary cementitious materials, okay. So such materials include fly ash, GGBFS, granulated blast furnace slag, etc. Use of such materials as partial replacements for Portland cement lead to a slower rate of this one setting and of early strength gain to the concrete, which is desirable in hot weather concreting, okay. So that will lower the rate of setting, okay, and of early strength gain to the concrete, which is not desirable in hot weather, okay. In cases where rapidly setting cements are being used, SCMs may be used to improve performance of concrete because it will lower the setting time and early strength, okay, gain. So use of fly ash may also reduce the rate of slump loss of concrete under hot weather conditions. So fly ash addition has an added benefit because it also lowers the loss of slump, okay, loss of slump rate, okay. So that is also lowered using fly ash in hot weather conditions. So these are some of the mineral admixtures, okay. So apart from there are some chemical admixtures also which can be used. So admixtures that have both water reducing and set retarding properties are used widely under hot weather conditions, okay. So that will increase the this one setting time and reduce the amount of water required, okay. So that will in a way increase the strength, okay, because of the relation, and they can be used to avoid strength loss as we just discussed that may otherwise result from high concrete temperatures. And and because of that super plasticizers are used to produce flowing concrete under hot weather conditions, and this improved property of concrete permits a more rapid placement and consolidation of concrete. So basically use of chemical admixtures will increase the flowing characteristics, okay. So as the flowing characteristics will increase, the slump loss will be reduced, okay. So that will result in a more rapid placement and also of concrete consolidation, okay. So by using these properties, it can counter the adverse effects of hot concreting. So here also we can use some storage facilities where aggregates can be saturated and kept in some moist condition, so that this it does not take much water during casting. So let us see the scenario of proportioning, okay, in terms of hot weather concreting. So ingredients in their proportions should be such that they contribute positively to the satisfactory performance of concrete under hot weather, okay. Cement content should be as low as possible, but obviously be such that strength and durability requirements both are met, okay. In general, concrete should be proportioned for a slump of not less than 75 mm to permit prompt placement and effective consolidation in the form, because it is going to decrease, okay. So it should at least be 75 mm, okay. Performance of concrete mixtures proposed work should be tested under more specific conditions representing the delivery time and environment expected at the project, okay. So these are some of the conditions that has to be kept in mind in proportioning point of view, okay. So from the production and delivery point of view, let us see how it is affected. So production facilities and procedures should be capable at production rates required by the project. Satisfactory control of production and delivery operations should be assured. Concrete plant and delivery units should be in good operating condition. Any stoppage or mechanical breakdown can be more serious under hot weather conditions than in moderate weather, okay, because of the this one because of the rough weather and because of wearing off. Okay, so these problems, due to mechanical breakdown or stoppage, it can be far more serious. Okay, and that will further increase the shrinkage and cracks. Okay, and then in hot weather concreting operations, concrete placements may be scheduled at times other than during daylight hours. So this can be a smart idea. Okay, so the maximum temperature it can be attained at daylight hours, but if we if we work at some other time, okay, say in the evening or at night, okay, so the ill effects of hot weather can be drastically countered. Okay, so this is a very out of the box and smart idea. So temperature control of concrete. So how can the concrete temperature be controlled? So there is a thumb rule. Okay, so the temperature of concrete of usual proportions can be reduced by zero point 0.5 degrees centigrade by any of the following techniques. Okay, so if we reduce cement temperature by 4 degree, it can be reduced by zero point 0.5. Okay, the concrete temperature. If water temperature is reduced by 2 degrees centigrade, again concrete temperature can be reduced by zero point 0.5. If the temperature of aggregates is reduced by 1 degree, again the concrete temperature can be reduced by zero point 0.5. Okay, so all this can significantly reduce the temperature of concrete by half degrees. Okay, and most important is the aggregate, because even a reduction of 1 degree can reduce the concrete temperature by zero point 0.5, and that is because it is occupying the maximum volume. Okay, volume as well as mass, around 50%, okay, of the total concrete. So aggregate. Yes, yes, yes. Cement temperature, like if you use some this one mineral admixture, okay. So mineral admixture will result in lowering the rate of hydration. Yeah, lowering the rate of hydration. Okay. So if the lowering the hydration rate is lowered, then the exothermic reaction will also be lowered, right? So say for example you use 100 kg. Okay, so 100 kg resulted in, say for example, say it resulted in 40 degree. Okay, so instead of 100 kg, if you substitute it by say 60 kg of mineral admixture, so definitely the 40 kg will not give 40 degree. It will be much lesser, around 25 or 30 degree. So that way you are reducing the temperature. Okay, so those techniques can be used. Okay, because you are accounting for the total, okay, total amount of concrete. Okay, not individual cement. Okay, so those are, so those are some of the techniques by which we can use this one. We can go for the cause of reduction of hot weather. Okay, we can counter the ill effects of hot weather. Okay, so aggregate temperature should be kept as low as possible, because it is the maximum, okay, concentration. Okay, it is in the maximum concentration, and that can be possible by means such as sprinkling and fog spraying of coarse aggregate stockpiles. Okay, and also like cementing, like if we use some ice, okay, ice in place of water, if we can use ice. Okay, so that can also maybe although it can also help in reduction of water as well as the reduction of temperature of cement. Okay, during the hydration process. So that way many things can be done. Okay, so yeah, so now let us see how we can go for batching and mixing. Okay, so how the batching and mixing process affects. So the procedures under hot weather conditions are no different from good practices under normal weather conditions. So operators often batch concrete in a drier condition than desired to avoid producing a slump higher than specified. A small water addition may be needed at the job site. Okay, so hot weather conditions need to split the batching process by batching the cement at the job site, or layering the materials in the mixture drum at the plant to keep some of the cement dry, and then mixing the concrete after arrival at the job site. So these are the things that can be done. Okay, so the mixing drum can be used at the plant. Okay, and some of the cement, okay, so those can be split. Okay, and those can be mixed at only at the job site. Okay, so the concrete, okay, it will have some lesser temperature as compared to those which have been properly batched and mixed at the plant itself. Okay, so these are some of the few techniques. The amount of mixing and the speed of the mixture should be held to the minimum to avoid any unnecessary heat gain of concrete. Okay, specifications governing total number of revolutions of drum usually set a limit of 300 revolutions for truck mixers, because if you go for more, the heat required will also be more. Okay, amount energy will be more, and that will also result in heat. Okay, so let us now come to delivery. Okay, how the delivery can be adjusted. So the time lapse between start of mixing and to placement of concrete should be minimized. So this is one of the factors due to which it's better to batch the cement, okay, and mix it at the site instead of at the plant, okay, as we discussed in the last slide. So proper planning to coordinate dispatch of the mixer trucks with the rate of concrete placement, this is also required, so that firstly so that the process is efficient, and secondly this reduces the delay in arrival or waiting period until discharge, because more is the delay, okay, higher is the chance of getting the temperature getting higher, okay. Major placement should be scheduled during periods of lower urban traffic loads, okay, so that planning is more reliable, because otherwise it will be congested, and that will also, there is a chance of increasing the temperature or direct, it will be contact with the sun, okay. So these are some of the considerations in terms of delivery, okay. Now let us see some of the considerations in terms of placing, okay. So here are some of the planning which can be done in hot weather placements. So we need to firstly minimize the exposure. That's why it is very important to, the time lapse between mixing and placement should be minimized, because there is no there is no prevention to exposure. But here we can minimize the exposure to adverse conditions, okay. For that we can consider placing of slabs, after roof structure and walls in place, or erecting a temporary shelter, okay, at the time of construction, which does not allow the sun rays to fall directly on the concrete, okay. We can prepare for some ambient conditions, okay. We can mobilize protective measures according to local weather reports. We can expedite the placements, okay. We can prepare okay, we can do some preparations, okay, which can make the transport, okay, placement, consolidation and finishing, okay, as fast as possible, okay. So these are some innovative ways we can think about. And apart from that, we can, in case of flat work placement, the subgrade should be moist yet free, okay, of standing water and soft spots, okay. So that will not degrade the strength, as well as that will not take the water, okay, not increase the water demand. So these conditions can be, ways to optimize our placement conditions, and to counter, in a way, counter the ill effects of hot temperature, okay. Apart from that, we can also study how slump adjustment can be done, okay, to, cope up with the increase in water demand. So using actual materials and proportions, okay, slump laws between plant and job site should be established, okay. So that can be only done by trial mixes, okay. If on arrival at site the slump is less than the required minimum, additional water may be added, provided that the maximum allowable water content is not exceeded. So that this is basic, okay, basic rules. Use of chemical admixtures may facilitate adjusting required slump, as we studied in the last class. The performance of such admixtures in hot weather, including a tendency to promote segregation, should be independently verified, okay. So performance of these admixtures in hot weather, okay, and its tendency of promoting segregation, okay, these are some of the serious conditions we need to initially verify, okay, as per some standard codes, okay. So retempering, so this refers to the addition of water and remixing of concrete or mortar which has lost workability to become unplaceable or unusable, okay. So we need to retemper those, and any water addition in excess of the proportion maximum should be simply prohibited, okay. So that can be done by using some chemical admixtures, okay. Adverse effects on strength and other detrimental effects should be also studied, okay, because there may be some other conditions also related to the hot weather, okay, concreting. So apart from them, let us see how, on the curing and protection stage, okay. So concrete should be protected from high temperature, direct sunlight, low humidity and drying winds, as we studied, okay, just now. So high initial curing temperatures are detrimental, okay, because that will result in increase of thermal cracks, okay, to the ultimate strength to a greater degree than high placing temperatures. So this initial curing temperature should be as low as possible, and that can be done by lowering the rate of hydration, okay. Concrete should be carefully cured for at least the first 7 days, taking special precautions such as covering with waterproofing layers, okay, in cases when there is a large difference between the day and night temperatures. So here the to be guaranteed that the minimum strength is developed, so it should be carefully cured for at least 7 days, okay, taking special precautions such as water covering, like waterproofing layer cover, and especially in the case of higher difference. Okay, so that may also be an ill effect because of the freezing and thawing thing. Okay, so apart from that, let us go into some other curing methods, how it can be implemented in hot concreting. Okay, hot temperature concreting. So first, let us go to moist curing of flatwork. So this is the best method for developing the strength of concrete in case of flatwork and minimizing early drying shrinkage. Okay, ponding, covering with clean sand, kept continuously wet, sprinkling, etc. These are the ways how we can keep the flatwork moist. Okay, using curing. So that is the moist curing. Okay, directly implementing wet water. Okay, the wet curing. So how can we go to membrane curing? Okay, let us see that. So we can use of liquid membrane forming compounds. Okay, these are the methods of curing where job conditions are not favorable for moist curing. So this moist curing is the best way. Okay, because we need to simply add water. But if that is not possible, we go for liquid membrane, that is the membrane curing. Okay, so various types of liquid membranes can be used here. The membranes restrict the loss of moisture from the concrete. Okay, thereby allowing the development of strength, durability, and abrasion resistance of flatwork. Okay, and concrete curing of concrete in forms. How we can do this? Let us see. Forms should be covered and kept continuously moist during the early curing period. So during the strength development phases, early strength development phases, so it should be covered and kept continuously moist so that there is no impact of high temperature. Okay, so this is the example of membrane curing in concrete. The concrete is covered with an impermeable membrane after the formwork has been removed. Okay, so these techniques are basically although some standard ones are known like polythene and some materials, but mostly many are such like for mega structures which are used. They are mostly some industrial kept secrets. Okay, so those are some research ideas. Okay, which are implemented which can reduce the cost. Okay, but those are mostly secrets. Okay, industrial secrets. So these are the ways which we can counter the ill effects. Okay, and apart from that, let us see the testing and inspection ways. So frequency of inspection for properties such as slump, air content, ambient and concrete temperature, relative humidity, unit weight. So this all these parameters in hot weather conditions. Okay, so these parameters should be inspected very frequently. Okay, so that's why it should be higher, the frequency of inspection, than for normal conditions, because of the threats. Okay, because of the problems associated with hot weather concreting, mainly because of the cracks. Okay, simple experiments such as this one, measurement of the actual evaporation rate can be carried out to validate results and plan concreting operations. So this is measuring the actual evaporation rates. This is a very simple experiment which can be done anytime. So this can be used for validating our plan and making it more efficient. Okay, and similar at the same way plan the operations of concreting simultaneously accordingly. So after beyond that, we can take care. Okay, care should be taken in hot weather to maintain specimens at an appropriate temperature and for preventing moisture loss during their initial curing. Okay, so these are some fundamental things we have to keep in mind. Molds used should not be absorb water and or expand when in contact with moisture or when immersed in water. Okay, so these molds, okay, molds should also be tested. Okay, so that they don't absorb water or they expand. Okay, so that the concrete shape is disturbed, or that also results in some cracks. Okay, additional tests may be carried out to get data for strength under field conditions and milestones, curing regimes, removal of formwork, application of load, etc. Okay, so some additional tests also may need to be carried out for gaining all those data. Okay, so mainly all those are dependent on the trial. Okay, mixed trials. So here these are some of the illustrative examples which you can see. So here the subgrade has been dampened and yet it has been kept free of standing water. Okay, so this will lessen drying of the concrete and reduce problems from hot weather conditions. Okay, so this will not impact the strength as well as lessen the drying of concrete. Okay, and here is, if you can, as you can see, this is most probably this one membrane curing. So fogging cools the air and raises the relative humidity above flatwork. Okay, to lessen rapid evaporation from the concrete surface, thus reducing cracking and improving surface durability. Okay, so relative humidity is playing a big role in reducing the cracking, improving the durability, and also keeping the concrete cool. Okay, so that the heat is not affecting in development of cracks. Okay, so these are some of the this one ways how we can counter the adverse effects of cold weather and hot weather in special concretes. Okay, because it is special because of the temperature, because it is beyond the normal ranges. Okay, now let us go to some special topics. Okay, and find out the importance, right methods, and its specification. Okay, so these are some of the standard testing which are which have been done. Most of them we know only, basically compressive strength, slump, and all those, flexure and all those. So these are done as per the special codes. Okay, so relevant codes internationally. So here, as you can see, this trial, there are basically three stages. Okay, so first stage is a trial batch, which is done in laboratory. Okay, and that is that is done both for fresh concrete as well as hardened concrete. So that is basically the first stage. Second stage, this is also a trial batch, but this is done in site laboratory. So here basically we do the paperwork. Okay, so paperwork as well as the basic testing. Okay, here in the site laboratory we actually implement our ideas. Okay, so that is the second stage, and we really find out is it okay. Okay, and after that we if both are okay, both tests are okay, we go for mixed proportion. Okay, so we go for mixed proportion, and that also can be divided in two ways. Okay, first is the mock-up, that is the rehearsal before the actual construction, and second, if this is satisfied, we go for the real construction. Okay, so these are basically are the three stages of going for the concreting in special environment. Okay, so here these are some some rules specific taken from IS 516 specification, and here like they have mentioned compacting, how to do compacting, tamping, okay, by hand, and specimens by vibration, etc. So this we have studied more in our undergraduates. So yeah, so here as you can see, placing the place, it has been taken from IS 456. As you can see, the concrete should be placed and compacted before initial setting of concrete commences, and should not be subsequently disturbed. Okay, so this is the initial setting time. So as we all know, it should be well properly compacted to avoid honeycombing much before the development of initial stiffness, that is the initial setting time, and afterwards it should not be disturbed. So these are the very basic ideas. And as you can see here, it is again taken from 456. So they have mentioned some some entrant air percentages requirement for various nominal sizes, 20 mm, 40 mm, to ensure protection against freezing and thawing actions. Okay, so as you can see, 20 mm entrant air percentage should be 5 plus minus 1, and 40, it is 4 plus minus 1. Okay, and when concrete lower than grade M50 is used under these conditions, the mean total air content by volume of the fresh concrete at the time of delivery into the construction should be, so these are basically for grades lower than M50. Okay, for higher it should be again trial mixed and found out. Okay, so no mention of measuring air content of fresh concrete is maybe given here. So as per ASTM C231, these are some of the testing methods. Okay, so to go into to understand this, we have to go to this codes and understand how it is done. Okay, which is beyond the scope of this course. Okay, so basically if we can say, we can find that for a large project, determining the proportion of concrete is one of the initial first steps. Okay, so this exercise should be kept in mind. The material, this basically this exercise of proportioning and blending, mixing, so batching. So there it should keep in mind the material to be used, the conditions, the construction methods, etc. Sampling procedure needs to be formulated. There should be guidelines and specifications available which can be used as reference. Okay, but we have to review them by properly actually doing trial mixes inside. And also we always should have a healthy disrespect. Okay, so this is an oxymoron. Okay, healthy is a positive thing. If it is a healthy, it can be disrespectful, but if it is disrespectful, it can be healthy. Okay, so this is called as an oxymoron. Okay, so it we should always have a healthy disrespect for specification. Why? It is because it is healthy because it has the wisdom. Okay, so they have prepared it based on all the experiences they have gathered. Okay, but it should also be disrespected because this is not something etched in stone. Okay, or something which has been sung by some noble person. Okay, so it there is scope for some, some anomaly. Okay, some anomaly or some problems. So at that time it again has to be disrespected. Okay, that means it should be changed in case of need. So it should be healthy disrespected. Okay, all the specifications, and accordingly we have to plan our mixing. Okay, so these are main persons, the main people, okay, involved in the construction, that is the client, consultant, and contractor. Okay, each of them has a role to play, and if the specifications are good and complete, a greater chance of better quality construction. Okay, this is the mantra. So basically this mantra has to be kept in mind for concreting in this temperature, and for also normal. Okay, for every concreting, this is the mantra. Okay, so in sampling and testing and interpretation of results, we have to keep in mind the conditions of sampling, the methods of sampling, conditions of curing, how should the cubes be compacted. Okay, so these are the main conditions, and that is the reason why the sample should represent the real concrete. Okay, so whatever we do in the labs, okay, that those are under control environments. Okay, but we have to make it as realistic as possible so that it represents, the representation of the inaccuracies and the uncontrolled conditions. Okay, are simulated in the testing. So that is the thing we have to keep in mind. Okay, so at last we can see here some of the pics. Okay, we will through gallery we will show you. So we will study. This is a PQC material, that is a pavement quality concrete material unloading at the site, as you can see. Okay, so this is the PQC mix spreading at site. So this here the paver machine backside view when it is not in operation, as you can see. This is a concrete in vibrating panel. Okay, so these are the real site conditions. So here the mason's trolley. Okay, as you can see here after paver, so they are trying to finish. Okay, perform finishing. So here you can see texturing and curing machine TCM backside view when not in operation. So in the construction of road, so this is a texturing curing machine used. So here this is texturing and spraying of curing compound over PQC surface. Okay, so these are some of the criteria which they can use for altering the harsh environments. Okay, which they have used. Then here they have used for underwater construction concreting, they have used Tremi method. So here basically, as you can see, there is a hopper at the up, this one. Inside there is Tremi pipe section in the water, and at the seabed. Okay, so there is a concrete mass depositing. Okay, so the concrete has to be poured in the air, and it will pass into the water and go and deposit in the concrete as a concrete mass in the seabed. Okay, as you can see here. So basically this is the Tremi pipe, and it is surrounded by a steel cage. Okay, so that it is sturdy and nothing, there is no issue of leakage or something. Okay, so here you can see the examples of tunnel shotcreting. So here this one, the infrared curing is used, as we studied initially. So this is hollow basically, so that's why infrared curing is a very good idea for curing. Okay, so tunnel shotcreting, this is mainly used in heavy construction, and here they have poured shotcrete for shear strength. Okay, so shear strength has been increased by using the method of shotcreting. So here tunnel and convert shotcrete linings, as you can see here, they have shown here shotcrete by slope. This shotcreting has been done for protection of slope, as you can see. Here you can see these are some of the these are some of the pictures which show the curing and shotcreting and various other techniques. Okay, which can be used for adverse conditions, and using various adopting various curing and placement methods. Okay, so as all the criteria have to be taken into account using the very relevant codes and specifications. Okay, so here you can see slope stabilization. Okay, and here you can see hexagonal wire mesh. Okay, so all those are having some some advantages or the other. So yeah, so determining the strength of concrete for a shotcrete. So this is a panel for sample shotcreting. So shotcrete, say for example, we have to shotcrete. Okay, so there are various various criteria, okay, which have to be taken into account for standardizing the size, okay, size of the nozzle and everything. So basically, that will depend on the thickness of deposit, okay, the number of layers, the required for the deposit, the angle, distance from nozzle, okay, curing regime for panel, etc., etc. So these are some of the criteria, okay. And for testing, okay, we have to extract cores from the panel like this, okay, from some specific locations and test and find the acceptance, okay. So whether it is as per in accordance with the standard criteria, okay. So these are the some of the shortcutting methods and how they will take the from here only they will take the course and find the do the sampling and find the perform the test and see whether it is in accordance with the relevant codes. So finally, some possible design and quality control specifications can be seen here. A cap on the maximum acceptable temperature for individual materials is necessary. Okay, a cap on the maximum placing temperature is also important. The extent of temperature rise and subsequent drop can be a design parameter in the design of structures where heat of hydration is suspected to be an issue. Okay, mainly for hot weather concreting. A value of such as 30 degrees centigrade could be one such example. Okay, so uh, anything like if the structure is more delicate, okay, a value of even a 30 degrees centigrade, okay, could be an issue for temperature of 30 degrees centigrade could be an issue for judging the heat of hydration, okay, because that also may result in cracks, okay, and it will result in less structure, less strength, mainly in HSC, high strength concrete. So the peak temperature reach can be another design parameter, okay, a value such as 50 degree centigrade, okay, as a value as 50 degrees centigrade could be one such example. So extent of temperature rise say by 30 degrees centigrade is issue, and also the peak temperature as high as 50 degrees centigrade also can be like one of the parameters, okay. So these parameters we have to take in mind, okay, placement temperature, acceptable temperature, okay, material temperatures, and for those we can give a index, okay, which is called a thermal, we can coin a new parameter which is called a thermal cracking index, okay. So there we can define some equations by which we can take into account all those, okay, and try to find out whether the values are within some standard ranges which are acceptable, okay. So with this we complete the course contents with the third week problem, okay. So now let us briefly go to some of the problems, okay, which which are related to this week course, okay. So firstly, let us see this question, okay. Fill in the blanks in the following sentence using the base option, okay, from among those given. An increase in the curing period of the concrete results in dash in the concrete of in strength of concrete and dash in plastic shrinkage, okay. So as we know, the increase in the curing period, okay, that will result in the increase in strength, okay, because more is the curing, more will be the hydration, and if the hydration is done, okay, those spaces will will be filled in, okay, and that will result in lesser of plastic shrinkage, so decrease, okay. So it will be an increase in strength and decrease in plastic shrinkage. So as you can see here, increase and decrease. So let us go to the second question. Which of the following cannot be considered as an accelerated method of curing concrete? Okay. So which out of these four can be an accelerated method? Okay. First is steam curing at atmospheric pressure. Second is autoclaving, that is steam curing at higher pressure. Thirdly is infrared curing, and fourth is membrane curing. Okay. So steam curing, by the name steam, okay, this is a high temperature, and as we all know, high temperature will result in accelerated curing. Okay, so both the steam curing and atmospheric pressure and autoclaving, because both have steam, that will result in accelerated curing. Okay, so that is not that has to be cancelled. Third is infrared curing. Infrared is also resulting in high temperature, so that has also to be cancelled. Membrane curing, yeah. So membrane curing, as there nothing has been mentioned. So membrane curing directly, if the name, as the name suggests, can be an method of accelerated curing. Okay. So which of the following cannot be considered? Okay. So membrane curing cannot be considered directly as an accelerated method of curing concrete. Okay. So the answer is membrane curing. Third, yeah, yeah. Auto. Yeah, I think you joined a bit later maybe. This is nothing but autoclaving is similar to steam curing, only the difference is as pressure. Okay, so this is steam curing at atmospheric pressure, this is steam curing at high pressure. Okay. Okay, so that is the membrane curing. Third is, what is the maturity of a concrete block which is kept for curing for 10 days and the ambient temperature is kept constant at 10 degrees centigrade. So we need to find out the maturity, okay, for 10 days and 10 degrees centigrade. So for 10 days, as we know, one day is constituting of 24 hours. So 10 days will consider of 240 hours. Sorry. So it will be 240 hours, 10 days, and T naught is taken as minus 10 and T is 10 degrees. So 10 minus minus 10 will be 20, right? So 24 into 20 will be the maturity and that will be equivalent to 4800. Okay. So the answer will be 4800 degrees centigrade R. So as you can see, the answer is 4800 degree centigrade R. So fourth question, in the context of setting time of concrete, which of the following statements is correct? The setting time of concrete increases with an increase in temperature. The setting time of concrete increases with an decrease in temperature. The setting time of concrete does not depend on its temperature. The setting time of concrete will stop once the setting of concrete, sorry, will stop once the temperature reaches 0 degrees centigrade. So this, as we know, the setting stops when it reaches -7, as we studied in one of the slides. So this is incorrect. So this is cancelled. The setting time of concrete does not, so this is also cancelled. It depends, and how it depends is that more is the temperature, okay, so more will be the rate of hydration and lesser will be the setting time, okay, and lesser is the temperature, okay, more slower will be the rate of hydration and more setting time therefore will be resulting, okay. So that means the setting time of concrete will increase with an decrease in temperature. So the B, option B will be the second option will be the correct one, okay. So as you can see, the setting time of concrete increases with a decrease in temperature will be the right answer. So next, fifth question, which of the following conditions according to ACI 306 define the cold weather period from the point of view of concrete engineering, okay. So cold weather is defined as a period when for more than 3 consecutive days the average daily air temperature is less than 0 degrees centigrade and the air temperature is not greater than 5 degrees centigrade for more than one half of any 24-hour period. Second option is cold weather is defined as a period when for more than 3 consecutive days the daily air temperature average is less than 5 degree and air temperature is not greater than 10 degrees centigrade for more than one half of any 24-hour period. C option is cold weather is defined as a period when for more than 3 consecutive days the average daily air temperature is less than 0 degree and the air temperature is not greater than 15 degree for more than one half of any 24-hour period. And the D option is cold weather is defined as a period when for more than 3 consecutive days the average daily air temperature is less than 5 degree and the air temperature is not greater than 20 degrees centigrade for more than one half of any 24-hour period. So if you remember, in one of the slides we have defined what is cold weather, and that is nothing but this one. The average daily air temperature is less than 5 degrees centigrade for more than 3 consecutive days, and in there at a continuous stretch of 24 hour, okay, no at least at least one half, that is more than 12 hour, okay, it is not greater than 10 degrees centigrade. So if the average daily temperature is less than 5 degree and more than one half of any 24-hour stretch is not greater than 10 degrees centigrade for more than 3 consecutive days, so that can be considered as this one, cold weather period, okay. So the second option will be the correct one, okay. So as you can see, cold weather is defined as a period when for more than 3 consecutive days the average daily air temperature is less than 5 and the air temperature is not greater than 10 degrees centigrade for more than one half of any 24-hour period, okay. So next, let's go to the sixth question. Which of the following option is not recommended in cold weather concreting for achieving strength in stipulated time, okay. So there is a decrease in water demand, okay, and also decreased rate of slump loss of the concrete, okay. There is an increase in water demand and decreased rate of slump loss of the concrete, okay. There is an increase in water demand and also increased rate of slump loss of the concrete, and or fourth one, there is a decrease in water demand and increased rate of slump loss of the concrete, okay. So as we all know, hot weather concrete will result in higher evaporation, okay. So higher evaporation results in higher water demand. So either it will be B or second or fourth option. Okay, sorry, second or third option. Okay, and also we know this one, due to higher evaporation. Okay, so the rate of slump loss will also increase. Okay, so that means it will require an increase in water demand, as well as it will also require an increased rate of slump loss of the concrete. Okay, so the third option will be the correct option. Okay, so as you can see, there is an increase in water demand and also increased rate of slump loss of the concrete. Okay, so let us go to the eighth question. Which of the following statements appropriately describe the effects of hot weather concreting in hardened concrete? Okay, so there is a possibility of lower 28 day and later strengths and increase in permeability. Secondly, there is a possibility of lower 28 day and later strengths and decrease in permeability. Thirdly, there is a possibility of higher 28 day and later strengths and decrease in permeability. Or fourthly, there is a possibility of higher 28 day and later strengths and increase in permeability. So as we have discussed in the hot weather concreting definition, so there is a possibility of lower 28 day and later strength as well as an increase in permeability. Okay, so this is mainly because of improper this one improper water content, as well as lower improper water content, as well as lower hydration. And increase in permeability is mainly because of the development of cracks, basically three cracks: plastic shrinkage, drying shrinkage, and thermal shrinkage. Okay, so first option, that is there is a permeability of lower 28 day and later strengths and increase in permeability. Okay, so that will be the correct option. So yeah, so you can see there is a possibility of lower 28 day and later strengths and increase in permeability. Okay, so ninth question, which of the following is not recommended while working with concrete in hot weather? Reducing the temperature of concrete by cooling aggregates and water, use of slower hydrating cements, use of supplementary cementitious materials such as fly ash, or use of accelerating admixtures. So which is not acceptable or which is not good for hot weather? Okay, so not recommended. So basically use of SCM such as fly ash. So this is important because this is good alternative, because it will it will reduce the amount of cement hydration. Okay, so which will reduce the amount of heat generated. So this is acceptable, recommended. Use of slower hydrating cements is also recommended. Why? Because that will reduce the amount of hydration, resulting in reduced amount of heat generation. Thirdly, that is also recommended. And then reduction of temperature of concrete by cool aggregates and water, this is also recommended. Okay, so all those this will reduce the thermal this one crack. Okay, so all those three are recommended, but use of accelerating admixture is not recommended. Why? Because that will further increase the amount of heat generation. Okay, so the D option will be the correct one, fourth option. So as you can see, use of accelerating admixture is the correct one. Okay, so last question is, in the context of shotcreting, which of the following statements is true? The cement content in shotcrete is relatively higher, and smaller size coarse aggregates are used in shotcreting compared to normal concreting operations. Second, the cement content in shotcrete is relatively lower, and smaller size coarse aggregate are used in shotcreting compared to normal concreting operations. Third, the cement content is relatively higher, and larger size coarse aggregates are used in shotcreting compared to normal concreting operations. Or fourth, the cement content is relatively lower, and larger size coarse aggregates are used in shotcreting compared to normal concreting operations. So as we just saw in the gallery pictures, so we can see that shotcreting is done in through a nozzle. Okay, a pipe, and through the nozzle. So as you can see, that is only possible, okay, when the cement content will be high. Okay, fine content will be high, and also the small size of coarse aggregate is lower. Okay, so if this is less, okay, so that the filling material will be less, and if this is more, okay, that will also lead to segregation, because the concrete is traveling through a pipe. Okay, so that's why the cement content in shotcrete is relatively higher, and smaller size coarse aggregate are used in shotcreting compared to normal concreting operations. So the first option will be correct. Okay, so as you can see, the cement content in shotcrete is relatively higher, and smaller size coarse aggregate are used in shotcreting compared to normal concreting operations. Okay, so yeah, so basically with this we have come to the end of this week class. So basically we studied about the types of curing, what is curing, and we started our discussion on special concrete. Okay, basically from the point of view of temperature. Okay, so from that we found that through temperature we can segregate two types of concrete, concrete beyond the ranges, okay, which is lower than the normal, that is called the cold weather concreting, and which is higher, which is known as hot weather. Cold weather results in, increasing the size of the pores, okay, due to the freezing of the water. And hot weather results in cracks, okay, development of cracks, and increase in permeability, also increase in water durability, water demand. So to counter those effects, various techniques as well as curing methods need to be applied. So yeah, so basically these specifications need to be followed, such as ACI 306 and various other, which talks about this with along with the testing of the materials, okay, so that we get the proper behavior as well as the performance of concrete which we intended during design, okay. So with this we come to the third week course. So yeah, yeah. No, basically there is no, as such there is no hot weather, cold weather IS provisions provided. Okay, so basically we are basically still we are following the IS 456, which is from 2000. Okay, 2000 cold. Although some relevant criteria have been mentioned, like environment conditions, and some some specifications have been, some main some criteria have been mentioned, like what is the maximum cement content, okay, what is the minimum water content. All those criteria are mentioned, but dedicated code is not available till now. That is for the future, okay. Yeah, definitely, because we are staying in India, right? So because we are staying in India, if you like the thing is that you can go through any codes, okay. There is no liability or near problems following any code, okay. But if anything happens, like if anything is happening, or like any issues are there, okay, for which you need to you need to go in court, okay. So the code will only support the provision which is then specified in the IS provision, because it belongs to India, okay. But apart from that, you can go through any codal provision. You can design or innovate your design, okay, by for initially designing based on the IS provision, and then accordingly modifying it what you have learned by going through the US or other some relevant codes, okay. But when it comes to when it comes to any fighting any lawsuit or something, okay, only the IS code will help you, okay, nor American code or nor some British code. So that's why it's better to use IS code, okay. Yeah, 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 yeah. I did not get your point. Can you please explain once more? Okay. Huh. Hmm. 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 Question. The answer is because answer is related to the term which I just told at the end. Na? It's called healthy disrespect. Okay. The thing is, because we have to accept the codes, okay, based on the criterias they have used, okay, like the temperature condition, the geographic condition, topographic condition, okay. But it is not something etched in stone, okay, as I mentioned in one of the slides, okay. So it is not that, okay, what they have mentioned is 100% true, okay. So that may be useful in US, but there may be some criteria which, like which are not possible in implementation in India, okay. So those are the reasons why till now also we are still following the IS 456 2000, okay. It may be various issues, okay. So Yeah, so that's why, we have to accept everyone. Okay, that is the beauty of the various sports. Okay. Okay. So, okay, welcome. So, okay, then, with this we come to the end of this session. Hope you have a great day forward, and let us meet in the next class. Okay, next Sunday, 6 to 8 p.m. With this I would end my this one. Bye.